So Patty, how are we looking so far? Does everything look good?
Yeah. I forgot I wasn't Z scaled. I was worried because I couldn't see the star very bright, but now yeah, you can see the trace. I'm just downloading the first images just to try and run some checks on it initially. Yeah, everything looks good.
So while we're kind of getting started, I will share one of the screens that we're looking at.
Perfect.
I'm seeing aglow emission and aglow absorption. I see these dark bands.
Oh, yeah.
Not aglow absorption, atmospheric absorption, I guess.
Oop. Oh man, VNCing, resizing windows during VNCing takes some finesse.
Not a US university science.
Exposure complete.
So Patty, maybe we'll just take a look at the first couple images to make sure that we're on track, and then we could start the session.
Yeah, perfect. Yeah, they're downloading now. So
Yeah,
my download's like slower than usual though.
Is it?
Yeah. Like I just downloaded the calibrations and it took like for 40 FITS files, it took like, I feel like over a half hour.
Oh wow.
Yeah. But now it's taking the neuroscience science ones. So
I'll be grabbing them too, so hopefully one of us will get there relatively quickly.
sweet.
Mine's pretty quick actually. It's about 5 seconds per file.
Oh wow.
I'm a bit closer though.
Yeah, mine's averaging like, yeah, that probably makes a difference.
Yeah. See Monica K out the window, so it's just gotta come from there.
Yeah. Yeah, between like 45 seconds and a minute per file. So it'll take me like 10 minutes to get everything.
Okay. No worries, I'll take a look at the script.
Cool. I'm just gonna run to the bathroom. I'll be right back. Brian, are those cookies from you?
Yeah, they are.
Good.
Not from behind Roger, I don't think.
Oh, yeah.
No cookies in Los Altos.
Sadly, yeah.
Sadly.
Or I guess that's a good thing, right?
Give and take, yeah.
Yeah.
Exposure complete.
I wonder what this guy is. Southern Street.
It actually looks pretty dang good, Betty.
What does? Oh, this?
Yeah, it looks amazing. So
Yeah.
I could run the script, but it looks like we're doing all right now.
Sweet. Awesome.
So I think
Yay.
I'm gonna start just get the commands up and running so that we're ready to go, and then we can
Awesome.
start the session.
Sweet, sweet.
Do you dither along the slit and then, is this a difference between those two images like that? Or two spectra like that?
Yeah. Yeah, this is just
Okay.
the difference between the last two images.
Gotcha. And how much is the throw along the slit? Is it a few arc seconds?
0.7 arc seconds.
That's small. Wow. Okay.
No, I think actually, Patty, so the nod, so you did the edit params in the
Oh,
on the Mossfire desktop GUI. So
Yes.
and I think you have a nod amplitude there. It says I can actually switch to that screen.
yeah. 1.2. Yeah. Sorry,
Oh,
Roger. I
okay.
was.
No, that's fine. That's fine. So it's
lost.
3 times the full width half maximum. It looks okay. So yeah, it's clear of itself.
Mhm.
That's very good.
Yeah,
Okay.
so tonight, yeah, that's 3 times the full width F max for a point source.
Yeah.
We're hoping to keep it that way. Although
Are your galaxies more or less point sources in this case?
yeah, so
More or
the
less.
half-light radius of these things, something like 1 to 2 kiloparsecs circularized. So at Redshift 7, that's effectively a point source.
I see.
Exposure complete.
So are these dark ones absorption bands?
Which dark lines?
The vertical ones? The skylines?
Is that the lack of emission lines or is it absorption? That's what I wasn't sure.
Yeah. Yeah, I'm not sure what this, like the darker traces.
I must be on a different VNC screen than the one we're seeing, right?
Oh, sorry. Yeah. I'm
These
looking at
ones, these ones.
Yeah,
are
Yeah,
different.
that's
I just reshared.
my bad.
So I'm guessing the certain emission lines got stronger between the, or stronger or weaker between the two exposures. Is that what we're seeing
Oh,
here?
yeah, because it's the difference. Yes, this one.
Yeah, so we're
Okay,
probably
yeah,
seeing a lot of
most-
variation in the lines as a function of time. It's also, we're still, the atmosphere is still changing because of the sunset, and so probably lines are kind of going all over the place. Hopefully things will settle down over time. But yeah, that's a pretty marked depression in the signal there. It's an amazing change over the course of 2 minutes.
What wavelength range are we looking at here on the screen? Roughly.
So this is
1.4 to 1.7 microns, I think.
Okay, so H band.
Yes, yeah.
exactly, yeah. Okay, Patty, I'm more or less set up. It would be awesome. I unfortunately have to download the bits files to my UC Davis computer and then run it over there. So if it's easier
Okay.
for you to run, it'll be a little bit tricky for me to juggle all of that. So
Oh, yeah,
it'd be
for
awesome
sure,
if you
for
can-
sure.
you can do it.
Yeah,
Um,
I'm almost done with with number 49, so.
All right, if it becomes too painful, just let me know. I just have to copy it over to UC Davis computer.
No,
and then copy
this
to my
will be
local
super
machine.
easy for me. Yeah, no.
Sounds
it'll
good.
be
Okay, well, I
fine.
think we can get started. So, aloha. Thank you, everybody, for joining us. My name is Brian Lemo. I'm a scientist, staff scientist at the Gemini North Observatory, which is an observatory just southeast of the observatory that we're using right now, Keck 1 on Mauna Kea. I am not on the summit of Mauna Kea. I am in Hilo, Hawaii, which is just down the mountain. I can see Mauna Kea, not right now, because Hilo is usually cloudy, but I can see Mauna Kea usually in the morning from my bedroom, where I'm observing right now with Patty. So Patty, do you want to introduce yourself real quick?
Yeah. Hey guys, I'm Patty Wolin. So I'm a PhD student in astronomy at UC Davis. So I'm at our remote observing room now. Basically, we can control the telescope from wherever we are, which is awesome. And yeah, I'm working on my thesis looking at basically some of the first galaxies that form in the universe. So that's what we're looking at tonight. Yeah. And really excited because the conditions are really good. So hopefully we'll actually get some good data today.
And then we have another scientist on the call that will be hanging out with us for some period of time tonight, joining us from California, Raja Guhatakarte. Raja, did you want to introduce yourself?
Sure, I'd be happy to. So I'm at a different UC. I'm at the University of California, Santa Cruz. And I have, sorry, I've known Brian for a very long time. I've known Patty for a little bit. And they were kind enough to invite me to be part of this observing session. My main reason for being here is really to be part of the Shadow the Scientist session and to really try to understand how we can best combine two things, getting the science done on the telescope while having people who are not part of the science team, eavesdrop, take part in the session, and get something meaningful out of the experience. So this is something that Brian and I have been working with a few others to to build this sort of idea up, the Shadow the Scientist idea. So yeah, so and the other connection is Brian and I have known each other for a very long time because Brian was an undergraduate at UC Santa Cruz, and he and I did research together many years ago.
Many years ago. Not
Yeah.
well, not too long ago. Only a couple decades.
Yeah, nearly 20 years ago, right?
And since we're going to be talking about 10 million year timescales tonight or longer, then I guess not too long ago, cosmologically, anyways.
Yeah.
Yeah, so we're observing on Keck 1, which I said, so that's in the summit of Mauna Kea. And Raja has run Shadow the Scientist sessions on a lot of different telescopes. 2 on the summit of Mauna Kea, well, actually 3, I guess. So the 2 Keck telescopes, Keck are twin telescopes on the north summit of Mauna Kea, I guess North Plateau. So those are 10-meter telescopes. The primary mirror aperture is 10 meters. We've also run it on the Subaru telescope, which is not run by the company Subaru, but is the National Astronomy Observatory of Japan. So the National Telescope of Japan. It's on the summit of Mauna Kea right next door. It's a neighbor of Keck 1 and Keck 2 on the North Plateau. And Raja's also done Shadow the Scientist sessions and is doing more in the fall with the Lick telescope, which is on Mount Hamilton, just outside of San Jose in California. So tonight we are looking at super distant galaxies, or we're attempting to anyways. And we're doing so using a gravitational lensing technique. So we're looking behind a very massive conglomeration of galaxies in the semi-distant universe. So Patty, do you know what redshift the cluster we're looking at is?
That's a great question. No, I thought I had some way to pull it up, and I don't have it off the top of my head.
I could grab it, but I'm guessing it's like redshift 0.5. So it's probably,
Yeah.
you know, I don't know, let's say, yeah, maybe a third of the way to the edge of the observable universe. And we're looking for galaxies that are about, let's say 12, 13, so 13, 14s back to the edge of the observable universe. So we're looking at the very first galaxies we're attempting to look at the very first galaxies that formed in the universe. And we're trying to understand their physical properties. And the reason why we're looking behind this massive cluster is because so this cluster of galaxies, this conglomeration of galaxies, bends light in such a way to magnify distant sources behind it. And so these galaxies, which are very, 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 very faint, that take many, many hours of observing on a 10-meter class telescope to even get a hint of them, you need this assist of a lens, so a magnifying glass, to be able to really understand their properties well. So we are looking at galaxies that are probably 10 to 20 times fainter than the Milky Way, but at a distance of 13 billion light years. So very, very far away. And what you can see on the screen that I'm sharing right now is Patty's moving around. So this is our one of our 4 control panels for our instrument. The instrument that we're using is called MOSFIRE, which is a multi-object spectrograph, which is looking in the near infrared, so not in the visible range of light that we normally see, but in the near infrared, so like thermal. And Patty is looking at our image. So basically what we're doing, actually I can bring up a different screen. Here we go. So this is what's called a slit mask. And what we're doing, you can basically think of the telescope as being above the screen here, and the detector, the thing we're using to collect light, to be just below the screen here. And so we have a bunch of slit slides. So basically they're pieces of metal that move like this. So each one of these vertical or horizontal rows is a set of 2 slides that move like this in the path of the light that's coming from the telescope. So we point the telescope in a certain location, and this location is dictated by where we want to look. So this particular cluster of galaxies, and then we want to select certain types of objects that we're interested in. So this could be stars that are kind of used as calibrators for us. These could be galaxies that are within the cluster of galaxies, or these could be these really distant galaxies at 13 billion light years. And so the galaxies, or sorry, the things that appear as big red circles here, those are our guys. So those are the ones that we really want to see. The other ones that are a little bit smaller, so these blue small circles, these are potential galaxies. So we haven't confirmed them yet, but they're galaxies that are potentially at a distance of 12 to 13 billion light years. And then we have these vertical lines here. These are objects which are probably, Patty can say better, but they're probably within the cluster or something like that. They're just objects that we're, trying to get some information on. It would be great to get some information on, super nice, but they're not our primary objects of interest. So we can target all of these at once by creating these, moving these bars around in some way. So these configurable, they're called configurable slit units. So we move them. Each one of this, actually I can share another screen. Let's see here. Okay, so this is now the third screen of our setup. So you can see this is pretty complicated. There's a lot of buttons and stuff, and we get lost a lot of the time too. But if you can see over here on the left, I don't know if it's big enough on your screens to see, but you see the same set of horizontal lines, and then you can see these green vertical lines. So these are our slits. This is where we allow the light to enter. These are where we think our galaxies and stars will show up as the light from the telescope reaches this part of the instrumentation. And so these green vertical lines are all locations of potential stars, galaxies that we want to target. And so we allow the light to pass through these slits. And then we have something that disperses the light. So basically makes a rainbow out of the light, again, in the near infrared. So this is nothing that we can see, but the detector behind it. So this, basically camera detector behind it is very sensitive for near infrared light. So we disperse the light. So just a rainbow of colors in the near infrared. And then we're looking for particular signatures from particular elements coming from these galaxies. And so right now, we actually got all set up before the session started. We got our telescope pointed where we wanted to go. We got our telescope focused.
Complete.
And we got aligned on our target. So the way that we do that, maybe Patty, I can share the slit mask alignment tool, and you can run people through how we get aligned and how we know where in the universe we are.
Yeah, you're switching over to that one?
Yeah.
Okay, cool. Sweet. Okay, so yeah, like Brian was saying, we have to basically, the stuff that we're looking at is super faint. So in order to focus and make sure we're looking at the right thing, we put bright stars on the mask, and we make what's called an alignment mask where we have 5 stars. So if you look in the leftmost screen here, you can see in that image, those 5 white boxes. So that is where we center our 5 stars during the alignment stage. So basically, we open up these little boxes in our slit mask where we want those 5 stars to be, and we take a picture and we make sure that the stars are perfectly centroided or centered right in the middle of those 5 boxes, because we can't actually see the galaxies, like the stuff that we want to look at, within 2 minutes, which is how long each exposure is. So we have to use bright objects in order to make sure that we're staying focused exactly where we want to be. So that's what we did before we started this set of exposures that we're doing right now. We made sure that all 5 of those stars were aligned. And then if you look over on this right-hand screen, if you see this really bright horizontal line going across there, that's basically the trace of a bright star that we have on the mask. So we don't keep all 5 of these bright stars that we use for alignment on the mask while we're doing our science exposures, just because we want to, keep the slits for more interesting objects than just stars. But we let one slit be a star just so we
You say that so derisively, Patty, about stars.
Stars are okay, but
Okay,
we don't
yeah.
need
We
5
kept one of
stars.
them.
Yeah, right. So we basically just need one so that after every 2-minute exposure we take, we look at it and we say, okay, the star is still there. So we're still where we want to be. And having the trace of that star also helps with a lot of the post-processing of images once we're done with all of our observations tonight. So yeah, this is every 2 minutes. Here's another one coming through. This is the raw frame that comes out, and you can see that bright white line going across it. So we know that our star is there, and that tells us that we're looking at the right thing, basically.
Yeah, so basically we've subtracted the image prior to this and the image that just came out. And so the image prior to this, the star was in this dark band here. So this is the subtracted off image. And the positive, so the white, that's where our star currently is. So we're just moving back and forth in between these 2 locations. And this is because there's a lot of background in the near infrared. So we want to subtract off all that background and just be left with the objects that are in our that are of interest to us, besides all these vertical lines, which are somewhat unavoidable to have in our data. Yeah, so just to give people an idea, as far as alignment goes, so this is a very highly precise process. We need to do, so our slit size, so the vertical slits that I showed earlier, the width of these slits is about 1 arcsecond, a little bit smaller than 1 arcsecond, actually 0.7 to be precise. And that may not mean anything to anybody, but so if you were to go outside, you hold your arm all the way out, you put your index finger out and you close one eye, the width of your fingernail there. So if you, let's say you cover up the full moon, so the width of your fingernail there is about 1 degree. So 1 degree is 3,600 arcseconds. So this is 1/3,600th of a fingernail at arm's length in the sky. And we need to do better than even that. So we have, so you can see in the screen here, we have these offset values, and it says 0.02, 0.02. This is 0.02 arcseconds. So this is 1/50th of an arcsecond. So it's 50 times 3,600 of a fingernail that we have had precision now. So incredibly small distances, and we have to be right on to make sure that we get all the light that we possibly can. Because even though we have a huge telescope, we have this cluster that's helping us out in terms of seeing these galaxies, we still want to get every single photon that we possibly can through our telescope and onto our detector. So I see there's some questions in the chat. And Patty, I know that you were going to show us a little bit about what we're observing tonight, and I see that Raja has his hand up. So maybe we can go over a couple of questions, and then we could show people a little bit more about the science that we're doing tonight. And start with Raja.
Yeah.
I was going to see what is the rule? How many lines per millimeter is the grating? I don't know the answer to this for this particular grating.
That's a good question. I'm gonna.
What's the name of the grating? That'll tell us.
It's the HK grading.
Oh, it's just called that. Okay.
Yeah. Let me check on the Mossberg website. It's a great question though.
Our project
The
has been
number
working.
120 is coming to mind, but I could just be making that up.
120, you said?
Yeah, but I don't know if that's
Oh.
the right one for this detector.
Aprajita has been working with our group on 1200G and 600 ZD. So
Mhm.
1200 lines per millimeter, 600 lines per millimeter, DMOS spectra.
Oh.
Yeah, the thing I was going to say is what you guys are doing here quite literally is you've got the world's biggest telescope, biggest optical telescope in Keck, and you've lined it up with some of the universe's largest telescopes, clusters. And it's really the combined power of these two telescopes that we're training on these very distant galaxies. No, the 5 alignment stars are too faint to be visible to the naked eye. My guess is these alignment stars are about 100 times fainter than the eye can see. Are they 15th magnitude? Or how?
Yeah, they're around 15, 16. Yep.
15, 16. So they're more than 100 times. They're 10,000 times fainter than the eye can see, because it's 10 magnitudes fainter than the faintest stars the eye can see.
Yeah, 10
And
more.
10 magnitudes is 2 factors of 100.
Yeah, I actually don't know the lines per millimeter. I know the R value, so that can help a little bit to understand. But I don't know, that information is not readily available on the Mossfire page.
Yeah, I can't find it either.
My guess is it's probably like 32 lines per millimeter. It's roughly the same dispersion that we have for one of the Gemini gratings.
Oh, wait, here, design requirements, 110.5 line per millimeter grading,
Ah, okay, okay.
if this is right.
This would correspond to low resolution because you want a lot of wavelength coverage, presumably.
Mhm.
Yeah, you still get a resolution of about 3 angstroms, something like that.
I see.
2-3 angstroms.
Yeah.
So Patty, there's a great question. I think it's the first question on the chat, from Evan. It said on the 12th, the 12th of July, one of the image which NASA will present of the James Webb Space Telescope first science observations will be a gravitational lensing effect of S max and then telephone number.
Yeah.
Has anyone here already have access to and studied this image? So this is a great question since we are using relics for some of these observations.
Yeah. Is this a relics cluster? Is this the one?
It's one of the relics clusters, I believe. Yeah.
Oh, I knew there was a relics cluster in there. I didn't know it was this one. Yeah, so that is a great question. So yeah, basically this cluster we're looking at now, and then we're looking at 2 more throughout the night. So we have 3 total for tonight to look at. And all of the clusters come from these big programs that basically for the past few decades have been using the Hubble Space Telescope, and they've been taking images of fields and identified these really massive lensing clusters. And one of the projects that put together a whole group of these lensing clusters is called RELIX. I think it's reionization era lensing something cluster survey. I don't know what that
I think that's right, Patty. Yeah, I don't know if there's another word.
Yeah, it might be lensing, like the ing is the
I think so.
yeah,
it's a little bit
unfortunately.
acronym.
Yeah, so the clusters we're looking at tonight are part of this relics survey, as well as that one that you said that JWST is giving one of the first images of. So yeah, the teams that we've been working with, like on a broad level, that's one of the ones that we've been studying. I even looked at this JWST cluster personally, but yeah, the people that we work with, like in all of our collaborations, this is one of the main clusters that we look at for science. So super exciting. That one of the collaborations that Brian and I are in is one of those first JWST images coming out. And then, oh yeah.
No, please go ahead. Patty.
Oh yeah, I was just going down in the chat with the questions. So Aparahito, if I'm saying that wrong, let me know. That's a different one that I sort of answered in a text, but they said, are the 2D spectra from separate individual galaxies? So yeah, that's a great question. So basically what Brian's showing on the screen now, the right-hand panel here with all of these bright vertical lines, that's what's called a 2D spectrum. So we're looking in the x-axis, we're looking in wavelength space. So you have bluer wavelengths or shorter wavelengths on the left-hand side of the screen, and then it goes to redder or longer wavelengths on the right-hand side. And then the y-axis here is spatial coordinate. So basically you can see that there are different horizontal bands, right? So every time that the vertical line ends, this is like multiple horizontal bands on top of each other. And that corresponds to the slit mask that Brian was showing earlier. So each of these bands here is one slit in the slit mask. And basically we have one object in each slit. So yeah, I think we have 30 something targets on this slit, if I remember correctly. So yeah, we're basically
Yeah, that
looking
sounds
at
about right, Patty.
yeah, like 30 something individual stars and galaxies, and each of them gets their own slit. So yeah, the spectrograph is really cool for that because you can bunch a bunch of things together and look at them all at once.
And then there was a question from Anand. Let's see. So I think Raja already answered Ari's question about the 5 alignment stars being visible to the naked eye. Not unless you're really, really, really good. So yeah, 10,000 times roughly fainter than the human eye can see. And Anand asked the question, which part of the sky are we pointed at with the telescope? So he's asking constellation and right ascension declination. So in fact, let's see here. So you can see on the screen that we're sharing, this FK5 value as I'm moving around, that actually gives the right ascension and declination. And for those of you who are not familiar with right ascension and declination, these are coordinates in the sky. So if you think of the Earth, and the Earth has latitude and longitude. And so if you just expand the Earth out and you imagine the stars as being on a celestial sphere, this alpha value, this right ascension called right ascension, corresponds to longitude, and this declination value corresponds to latitude in the sky. So, for example, declination 0 would be the celestial equator, and then there's a celestial prime meridian, which is the vernal equinox or spring equinox. So we're pointed now. So right ascension runs from 0 to 24 hours. So that's just how we do it for astronomers. So 0 is the prime meridian, which is the vernal equinox. And we're about halfway around the sky. So we're closer to the autumnal equinox. And then we're a little bit below the celestial equator at declination -11. And astronomers are not usually too good at constellations. This would be close to the ecliptic. And I think, if I'm not mistaken, it's Virgo is the constellation we're looking in. But Patty, you
That's impressive.
maybe know.
I know absolutely nothing about constellations.
Okay, so maybe case in point.
No help.
But right, so I mean, not to say that constellations aren't important, they're incredibly important. They're important for our designation system. And there's a lot of other reasons why we might pay attention to constellations. But we really work in numbers. And so this, RA-DEC, right ascension declination, this is what we're truly interested in, and this is how we can get the precision that we need, that I talked about earlier. So constellations are very big on the sky, and these are very precise coordinates that we can point to. So Patty, maybe I can stop sharing and we could go over some of the, it looks like we're doing great on the observations. Everything looks beautiful.
Yeah, I'm just about to run the thing. So 1 second. Here we go. Yeah, it looks like. Yeah, we're good. Yeah, the seam's bouncing a teensy bit, but it's centering around like 0.6, 0.7.
Oh, really? Oh, that's strange. That's
Yeah.
worse than I would expect. It may be that it's the fit there. I remember we were having issues with the fit before
That's true. Yeah. Yeah, it could be.
because yeah, I'm still seeing fairly good seeing at Gemini, so I would be surprised if we're
Okay, yeah. Yeah,
not
maybe
doing
it is
well.
just that code. Awesome. But yeah, I can show you guys. I have a few images and slides to talk about the science what we're doing. So Brian started to go over it
Closure complete.
in the beginning, but just to give y'all an idea of what we're looking at. Can y'all see that?
Yep.
Yes. Awesome.
Looks great.
Thank you. Sweet. Yeah.
And
So
by the way, for anybody that's in the session, feel free to write something in the chat. I'm happy to respond, or Patty will respond. Feel free to raise your hand to ask Patty a question, or myself, or Raja. Yeah.
Yeah, feel free to interrupt whenever. Cool. Yeah, so basically we mentioned this before, but so we're looking really, really far back in time to essentially when galaxies first started forming. And the main like reasons that we're trying to look at that is we want to get a better idea of A, what these galaxies looked like, and then B, basically what impact they had on the universe around them. So I'll say what I mean by that more in a little bit. And this image here is one of the ones, this is a relics cluster, right, Brian? Abel 370.
I don't think so. It's one of the Hubble Frontier Fields, I believe.
Oh, I thought some of those were in, okay. I didn't know those.
Yeah, I think relics is anything that's not, it was not in Clash and not in the Hubble Frontier Fields. I'm pretty sure this is a frontier field.
Okay, yeah, that makes sense.
But it looks a lot like any of the relics. This is just an amazing cluster, right? So it's like very, very massive, and you can see all the wonderful arcs there. So the relics clusters are usually a, small brother or sister of this kind of cluster.
Yeah, I like this image because it's a really good example of gravitational lensing that we were talking about earlier. So like Raja said, that's like the universe's best telescope ever is basically gravitational lensing. So you can see some objects like this that are just like, they're called arcs and they look like arcs, right? And there's some over here too. So that's basically, you have a ton of mass close by to us, or at redshift 0.5, which like Brian was saying is like a third of the way out to the edge of the observable universe. And this massive cluster will take the light from behind it and bend it all the way around it, so that when it hits our telescope, depending on the mass of the cluster and how it's spread out, some of the objects from behind it will get curved like perfectly into arcs like this. And then other objects behind it, like basically a lot of the ones we're looking at, will get maybe distorted a little bit, but most importantly, they get magnified. So even though they're intrinsically very faint, because of this gravitational lensing, they become a lot brighter so we can actually observe them. And still, we still have to look at them for hours and hours at a time in order to see anything. But the gravitational lensing makes it so that we can use ground-based telescopes to observe them. So yeah, just a rough idea of like how far back we are actually looking in time. Basically, this plot here is on an extreme skewed scale. But from the left to the right, you're going from the Big Bang over to the present day universe when we had all these beautiful like spiral galaxies that we see today. And where we're looking at is this era of cosmic history that's called reionization. So when I mentioned we want to see how these galaxies impact the universe around them, that has to do with basically this period of history that we call reionization. So essentially what's happening here is after the Big Bang, the universe was spreading out a lot, and as it expanded, things started to cool down so that eventually atoms could form. So what that means is that protons and electrons could bind together to form hydrogen, a few other elements. So at some point in time, what we call this cosmic dark ages over here, the universe is composed of almost entirely neutral hydrogen. So one proton and one electron together. But as you get forward to the present day, all the space or the gas around galaxies or the intergalactic medium is ionized hydrogen, meaning that the electrons were stripped from the protons. So there was some process in between the dark ages and today that caused this ionization to happen. Basically, really energetic photons are hitting those neutral hydrogen atoms and stripping them of their electrons. So this process is what we call reionization. And we have a pretty rough idea of when it happened. It finished at around a redshift of 6, which was when the universe was 1 billion years old. So the universe today is almost 14 billion years old. So we're looking way back at when the universe was less than 10% of its current age. And there's still like really big questions around this period of reionization. So we don't know exactly when it started, and we also don't know the properties of the galaxies or other objects that caused all of this ionizing, the ones that were emitting all of these high energy photons. So that's kind of why we're looking at these galaxies today, to hopefully get some insight on their characteristics and how they cause this process of reionization. So yeah, like I said, today we have all these beautiful spiral galaxies. I think this is the whirlpool, or maybe these are just simulated images actually. But when you think of galaxies, you probably might think of like beautiful like formed structure galaxies like this. The ones that we're looking at are pretty baby galaxies. So they've been forming for less than 1 billion years. A lot of them are maybe a few 100 million years old down to less than 100 million years old, which in galaxy terms is very, very young. So we're just looking at basically these tiny little blobs here, not beautiful, spiral structured galaxies. And they're so tiny and faint, which is why we have to look at them for basically as much time as we can, up to a full night per galaxy, in order to get enough photons from them to explore what they're actually made of. So I can kind of skip through this because we already talked about gravitational lensing, but here's another really pretty lensing cluster. You can see some awesome arcs going through here. But yeah, essentially we're not super interested in the cluster itself, but just the galaxies behind it that are being distorted and magnified by the lensing cluster. So yeah, the main science goals, like I mentioned before, we want to figure out what's going on with these first galaxies. So when I say properties, things like what elements are they composed of, right? So most of the universe before these galaxies started to form was hydrogen and helium. But as galaxies evolve, as stars go through the process of dying, they form new elements from fusion. So we're trying to figure out things like, that's called metallicity, is what elements are composing a galaxy, and other things like how many stars they're forming, basically the star formation rate, and other, there are a few other things, but those are some main ones. And yeah, we want to see what impact these galaxies had, basically how they influenced or were a part of reionization. And another cool thing is we are probably past this phase, especially with spectroscopy, because you saw we have individual slits that we only let a little bit of light in per slit. So we probably won't be finding any brand new galaxies with these observations. But in the collaborations that we're in, when you're doing imaging, like with Hubble and now with JWST, there'll probably be way more new galaxies found at these high redshifts during the start of the universe.
Well, Patty, I'll just jump in for a second and I'll say that because we have this awesome multi-object spectrograph, we're actually able to target, as you mentioned, like 30 objects at a time. And so we have like a couple of galaxies that we know the distance to, right? We know that they're 13 billion light years away, but then we have like 28 objects which we don't really know anything about. And so we should be finding hopefully some new galaxies tonight as well, on top of the ones that we already know about. I'm hoping, anyways.
Yeah, exactly. Yeah, that's a really good point. Yeah, so basically, in order to know exactly how far away it is, you need to have what I'll show later, an emission line from that galaxy. So basically, it emits photons at this very specific wavelength. And if we see that, and we know its rest frame wavelength, or basically the wavelength that would be if we saw it here on Earth, there's a really easy calculation based on the wavelength we see it at in our spectrum to figure out exactly how far away that galaxy is. So yeah, like Brian said, only a few of the galaxies we're looking at right now actually have those emission lines where we know exactly where it is. So hopefully we'll find a few more. We'll see.
And that, I mean, so just to give people an idea, I mean, those detections that we had were in the optical, not the near infrared. Yeah, so we used a different instrument on Keck. So sometimes it was the low resolution imaging spectrograph on Keck 1, the same telescope we're using now. And sometimes it was the Deimos multi-slit spectrograph on Keck 2, the neighboring telescope. But those observations, those were something like seven-ish hours just to get that one detection of these galaxies. Of course, we got many other galaxies because those spectrographs can target anywhere between 50 and 150 objects at a time. So even more numbers than the instrument we're using currently, though in the optical. But yeah, so even just to detect those galaxies, it took us 7 hours of time on the world's biggest optical telescope, in probably the world's best site for astronomy. And so then once we found them, then we're now targeting a second line, right? A second transition of a different element to understand those galaxies better. But it's taking us another 7 hours. hopefully we see something in 7 hours.
Yeah, hopefully. That's the goal.
But that's why we look, right? We don't
Yeah.
know until we look.
Yeah, exactly. Yeah, so this is basically just a view of what Brian and I showed earlier, where we have the slit mask, right? So you've seen a few different views of that so far with the the data that we're getting out right now. But this is what it looks like on an actual image of the sky with the slit mask overlaid on that image. So this is a Hubble image. This mask is not one of the clusters we're looking at tonight. We looked at this last time we observed. But basically each of these yellow boxes, you can kind of see them there. Each of those is the slit. So everything else is metal, right? And you only let light in where those little tiny yellow boxes are, because we don't want any extra noise bleeding in and overshadowing the photons from our little faint baby galaxies. So yeah, each of these, there's 30 or so of these yellow boxes here. The red boxes are the alignment stars that we were talking about earlier. And then one of these boxes, it's this guy on this mask, also has a yellow slit through it because that's a star that we put on the mask. So yeah, just to give an idea. And this image that I'm showing here is the Hubble observations of this cluster. So you can see that we have a pretty much wider field of view, not much wider, but wider field of view than Hubble does. So we're able to include, a few more objects on there, but all of our really high priority objects, the high Z ones, are going to be in this Hubble field of view because that's where we have the deepest imaging data. So that's how we pick them out. Yeah, and basically how that transfers over is this is basically the totally reduced data. So what we were looking at before was just raw exposures. So every 2 minutes, it takes another frame. That's what we were looking at. And this mask we see here is the result of hours of integrated exposing time. And this is after everything's been reduced. So at the beginning of the night here, basically in the afternoon, we took a set of calibrations. So it's basically used to factor out effects of the detector. So we took all of those, all of that gets subtracted or divided out, depending on what type of calibration it is. And then we stack together all of those individual 2-minute exposures in order to get this here essentially, which is a reduced mask. So like, for example, this really bright band here, this was probably our star that was on the mask. So if you see these horizontal bright lines here, that's going to be basically a bright object. And this trace is seen over all wavelengths. And that's what's called continuum, is when it has emission over like continuous emission over a range of wavelengths. And then, yeah, you'll notice these dark bands on top and on bottom of the bright trace. That comes back to what Brian mentioned earlier, is that we have to nod the telescope up and down. We switch off every exposure, and that's in order to reduce the noise from the sky, because the atmosphere is really bright in the infrared. There are just a lot of molecules in there emitting infrared wavelengths, unfortunately. So that's what these dark bands come from, is basically that nodding pattern. So what we're looking for in this data, so basically right when I'm done with the observations at 8 in the morning my time, I'll probably just start the reduction code and get her going, so that after I wake up tomorrow night, we can comb through it and see if there are any of these guys here. So this is a single
Looking like a
emission
true
line.
astronomer, Patty.
Yeah, exactly. Yeah, unfortunately, you have to be nocturnal every once in a while in astronomy. But yeah, so this is what's called an emission line. So basically just photons coming out at one single wavelength. That's an effect of quantum physics, right? So you have an electron dropping down from one energy level in the atom to a next one, and that emits a fixed amount of energy. So if we see those photons coming out, we'll get this bright blip at one wavelength. And yeah, what we're looking for is tonight is this emission line called C3, so doubly ionized carbon. And essentially this line, if we get it, we already have another really bright, well, not bright, but another strong emission line in all of these galaxies that we're targeting tonight. So the combination of the line that we already have, plus this line, the C3 line, will tell us a lot about the galaxy. And that's super exciting, because this line has only been detected in a handful of galaxies at the redshift that we're looking at. So it'd be really cool to get a few more for statistics purposes. So yeah, what else do I have? Oh yeah, so basically on the mask that we're looking at right now, we have 2 galaxies, 2 of our highest priority ones that we're looking at for C3 emission. So like I said before, we're looking at these tiny faint little guys. So this is what they actually look like on the mask. So hopefully after tonight, we'll have a little over 5 hours from tonight, and we already looked at it in April for 3.5 hours. So maybe we'll see something. We should find out by tomorrow, hopefully. But yeah, that's what we're looking at now. And just to give you an idea, I'll walk through this. I know it probably looks kind of complicated. But to give you an idea of why these galaxies are really exciting and what we're looking at in them. So basically, one of those that I showed earlier, oh shoot, okay. Here you go, this guy on the left here. So this is the cluster we're looking at, is called ARCS-J 1347. So the objects in them are just called ARCS-J 1347 point, whatever number they were in the detection sequence that we got them in. So this guy here has a different emission line that I mentioned earlier. It's called Lyman alpha. That's a hydrogen emission line. And we already have that one detected from, like Brian said, from either the DEIMOS or LROS spectrographs on Keck. And basically from the combination of that emission line and all the imaging that we have on this galaxy already, we have some information on the star formation rate. So like before, when I was talking about different properties of galaxies, one of them is star formation rate. So how many stars is it forming per year, essentially. And with this guy here, we can tell based on essentially the strength of this other emission line or combination of lines, O3 and H beta, which are just transitions in oxygen and hydrogen, that this guy here is forming a lot of stars. So it's a really high star formation rate, which is exciting because what this plot is showing here, so essentially on the x-axis, this EW equivalent width is just a measure of relative strength of an emission line. So we have the strength of O3 and H beta emission. And then on the left axis, or the y-axis, we have the strength of the line that we're looking for tonight, which is C3 emission. And all that this plot is showing here is that there is a linear relationship or direct correlation between the strength of this line that we have on the X, or we have an estimate of on the x-axis, and the line that we're looking for on the y-axis. So with this galaxy already from imaging, so it's from photometry, so not as precise as if we had these two lines from spectra, but we know that the O3H beta equivalent width or strength is somewhere at greater than 1300 angstroms. So on this x-axis, we're looking like right here. So where I put this red dot here, we're estimating that C3 is going to be at least 12-ish or so angstroms if we're following this linear relationship. So essentially, that I know those numbers don't really mean anything, but this is the process that we go through to figure out basically how long we need to be staring at this galaxy for. So there's, simulations and codes and things that we use in order to say, okay, how many hours do we have to be on this target in order to achieve or to see a line that has a strength of 12 angstroms or whatever that means. So those numbers don't have to mean anything for you guys, if that makes sense. But essentially, this guy has really strong star formation rate, and we already know the strength of this other line here. We can estimate the strength of this other line, which gives us an idea of how strong this line that we're looking for is, which basically all comes together to say, okay, we should look at this galaxy for 10 hours or so. That's probably the amount of time we would like to have on it in order to actually detect this line. So we're going to have like 5 to 6 hours on it. So if the line is a bit stronger than we predicted, then hopefully we'll see something by the end of tonight. But yeah, we'll see. And this is this galaxy is just one of, I think we have 7 that we're looking at in this campaign. So this is the last night of 3 nights that we had this semester to look for this C3 emission line. So yeah, that's what we're looking at right now. Hopefully we'll get something.
Thanks, Patty. But I mean, I think it's important to remember that even non-detection, so even things that we don't see, can be used to good effect to constrain galaxy properties. So you had that plot there where you showed the expected strength of the doubly ionized carbon emission relative to the doubly ionized oxygen plus neutral hydrogen emission. And so the relationship between all these different spectral lines tells us something. And you alluded to it about star formation rate, about the type of radiation that's being output by the galaxy. There was a really great question in the chat about black holes versus galaxies being formed first.
Oh, yeah.
And so these relationships can, if we're able to put limits on some of these emissions, we can say something about potentially black hole activity. So if a black hole is active within that galaxy, and we see in some galaxies these very high ionization lines like carbon-3 or helium-2, so singly ionized helium, these are very, very strong, and this potentially indicates some sort of very early on black hole activity. And so this is, we're really at the edge of our understanding here, and James Webb is going to be amazing for this, because James Webb will give us all these wonderful lines. Well, not us, because we didn't get time, unfortunately, on it.
Yeah.
But there'll be plenty of people that get really nice observations of galaxies at these distances, and all these wonderful lines that we know and love, that we're used to in the local-ish universe. James Webb's going to be able to see these at really, really large distances. And so the interrelation between all these different lines can really tell us something about the galaxy physical properties. But even non-detections give us some information about, so if we don't see C3, for example, in these targets, I think that may exclude certain types of black hole activity. And if we see C3 being stronger than expected, that may indicate that there's some additional component besides star formation that's happening in these galaxies that we'd have to go back to models and try to understand, which is your next part of your thesis, right?
Yes, exactly. Yeah. Yeah, because I was saying this is our last of 3 nights. So as of right now, on the 6 galaxies we've looked at, we haven't seen any C3. So we basically have upper limits on how strong the line can be. So yeah, that's what I'm going to be trying to do next, is interpreting these non-detections and what that actually means physically for the galaxies.
So in the chat, there was a couple of, well, one question and one really astute observation. So Kasora said, why are we looking for the C3 emission line in particular? I think that's a great question. There's lots of reasons why.
Yeah.
Patty, do you wanna cover that?
Yeah, sure. Yeah, so that's a great question. So essentially, when we're looking at these galaxies, there are a couple of things that limit what we can look at. So essentially, like I was saying, or we were talking about, once you get into the near infrared.
Oh, by the way, Patty, sorry. So I think we both kind of checked out of the observations, but I've kind of been keeping an eye on them. I think you have too. And
Yeah.
so I see that we're on our last observation of this cycle, so I'll do the wait and go if you want to.
Okay, perfect. Awesome. Thank you.
And we're doing 15 more repeats, yeah?
Yeah, that should get us to the end, I think. Cool. Yeah, that's a great question. Essentially, when you look at what the spectrum of these galaxies, oh, there we go, should look like, you see that there's some really bright emission lines. So I mentioned this other one, Lyman alpha. So that's pretty much the strongest emission line that we can see in these galaxies. There are some others that would be stronger, like O3H beta, but unfortunately, due to the redshifting of these galaxies, those emission lines get pushed way too far red so that we can't see them with ground-based observatories. So that's going to be something for JWST to look at. But yeah, essentially the first line that we targeted for all these galaxies is Lyman alpha emission, which is a little bit blue word of the C3 emission that we're looking at. And so all of these 7 galaxies have Lyman alpha detected in them. But the issue with Lyman alpha and why we want to get a second line is that the Lyman alpha line is a hydrogen feature. And we're looking at galaxies during the epoch of reionization, when the universe was still partially or mostly neutral hydrogen. And the Lyman alpha line gets easily absorbed and scattered by neutral hydrogen. So essentially what's happening out there in the universe is that the galaxy could be emitting this line, but once it leaves the galaxy and it enters the space of neutral hydrogen, it gets absorbed and re-emitted or scattered. So what happens there is you can picture this photon bouncing around a ton, like within the galaxy's perimeters, and getting more and more redshifted until it finally is able to escape and get to our telescope. So the end effect of that is that that Lyman alpha line that we have from all of these galaxies is slightly more redshifted than the galaxy actually is itself, because the Lyman alpha photons bounced around a lot more before they actually exited the galaxy's cloud or area and got all the way to our telescope. So this line that we're looking for now, C3, doesn't have that scattering effect. Oh, thank you, Brian. Yeah, so essentially the C3 emission would just leave and go right to our telescope. So the first thing that we get if we get a C3 line is the offset of how different was the redshift that we got from Lyman alpha versus the redshift that we get from C3. And that offset can give you a lot of information into the galaxies. So you can figure out basically the size of the ionizing bubble. So all these stars in the galaxy are emitting all these photons at once, so they carve out an ionized bubble around, the immediate perimeter of the galaxy first, and then that how reionization happened is kind of each galaxy carves out a little, well, how we think it happened, not 100% sure, but carves out a little ionized bubble, and you have a lot of galaxies doing that at all different places in the universe until eventually everything became more or less ionized. So if we know exactly how far those Lyman alpha photons are redshifted compared to C3, that gives us an idea of the size of that ionizing bubble. And also the ratio of strength of Lyman alpha to C3 can give you insights into things I was talking about before, like metallicity and composition of the galaxies. And the reason we do C3 as opposed to any other rest frame UV emission line is it's the second brightest typically after Lyman alpha. So we have the best chances of seeing it. But the strength of C3 compared to Lyman alpha is, I don't know, it's usually like what, around like 1/10 to 1/4 or so. There are some
Yeah,
estimates.
about
from-
that. Yeah. about
Yeah,
that.
yeah.
But there's a
So,
large scatter. So as you mentioned, the processes governing Lyman alpha are very, very complex. It's not,
mhm,
processes governing any emission are very complex, but what is emitted and what we actually see, there's a complicated relationship between those two things. And so Lyman alpha can vary for based off of the velocity of the velocity of the galaxy, so the different velocity components of the galaxy, what kind of environment it lives in, how many stars it's forming, how much dust is there. And so the relationship is very, very complicated between the what you see in terms of Lyman alpha strength and the carbon-3 strength, which is, as you mentioned, Patty, is basically unattenuated. So basically the emission that it comes out of the galaxy, besides dust and other things which control that, is basically what you observe.
mhm. Yep.
And then
Roger,
so Robert mentioned, so I mentioned about about the magnitude of these sources. So I said they were about 26th or 27th. And Patty, I guess you showed an image in your talk of a Hubble observation of these things. And
Mhm.
those observations, I'm not sure which survey they're from, but they're probably many hours on Hubble is my guess. And
Yeah.
Hubble is incredibly sensitive. And you saw that they're just basically little tiny blips. We just barely detect them in that image. And so I mentioned that these things 26, 27, about 100 million or a billion times fainter than we can see with the naked eye. And so then Robert said, rightfully so, that is incredibly dim, which it is. So they must be near the limit of being able to extract a spectrum. And so, yeah, we would have absolutely no chance at that. So, I mean, you can see in the screen that I'm sharing here, of course, the star that is something like 16th magnitude. So it's about 10,000 times brighter than the galaxies that we're looking at. We can see that just fine in a 2-minute exposure. But there's no way that we're going to be able to see the galaxies in just a 2-minute exposure. And as Patty mentioned, we're looking for just an emission line. So we're not even looking for, a nice, broad, bright horizontal feature like this, but we're actually looking for just a blip somewhere hidden in all these vertical lines here. And so it'll be in one of these slits, probably towards the middle of our slit mass. And so we have to know the precise location of that object. So we can't rely on being able to detect it. We have to actually know which slit we're observing it in and where along. So this is the spatial axis. So the slit. So Patty showed the picture where there was on the Hubble image, there was a rectangle like this. That was our slit. And so along this axis is the spatial axis, and we have to know precisely along that spatial axis where this galaxy is supposed to lie. So then we can just focus on the light there and create a spectrum. Otherwise, we'd have no chance at this.
Brian and Patty, I was going to just to add to what you've been saying, it's really difficult to go from something like an AB magnitude or any kind of magnitude of a galaxy to its detectability in a spectrum, because we're looking for emission lines. If we were trying to detect the continuum of the galaxy, there's a very well-defined relationship between the two, because what I'm trying to say is the brightness of the galaxy, whether it's in AB magnitudes or Vega magnitudes, is really sensitive to the continuum level. Like for the star, you're seeing the continuum, and the 16th magnitude is determined by the continuum of the star. for these galaxies, the continuum is hopeless to detect. And it's really how strong the emission line is that you can't really tell from the AB magnitude generally. So in this sense, until you take a spectrum, you really have no way of knowing how strong its emission lines are going to be.
Yep, excellent, Roger.
So a couple of other things I wanted to say. One is Arya and Anand have asked about whether the distant galaxies are gravitationally stretched out into arcs. In general, they're distorted. Magnification, the way gravitational lensing works is it preserves brightness per unit area. So the reason something gets bigger, reason something gets brighter is because it gets bigger in the sky. Its angular size grows. Surface brightness per unit area is preserved by gravitational lensing. So yes, indeed, they're distorted they're stretched, and they're generally stretched more in one direction than another, depending on the details of the lens. So yes, they're mostly, the distant galaxies are stretched into arcs or arc-like structures. I was going to ask you guys, Patty and Brian, whether I'm guessing C3 is a forbidden line.
Yes,
Yes.
it's a doublet. Yeah. One of them is forbidden, one's semi-forbidden.
Okay, so you wouldn't write it as a C with a normal 3. You would write it with a Roman numeral 3, and I'll write that in the chat. And its rest wavelength must be around 2000 angstroms, I'm guessing. I'm
Yep,
forgetting the exact wavelength.
1907, 1909. Yeah.
Okay, so
Good guess, Roger.
emission line doublet. Okay, so it's in the ultraviolet part of the spectrum, and the other thing is it's at a slightly longer wavelength than Lyman alpha, so it's a little less susceptible to the effects of dust absorption. Little less than Lyman alpha.
Yeah, that's a good point.
You said 1907 and 1909, right?
Yep.
Angstrom. And so here's the other cool part of this. So I've just put this in the chat, and that's how C3 is written. Square brackets for forbidden, and you'd put one square bracket on the right if it's semi-forbidden. It's an emission line doublet, ultraviolet part of the spectrum. What is really cool here is, let's round this number of 1900 into, it's close to 2000. You multiply that by 1 plus the redshift, this is redshift 7. So you multiply 2000 by 1 plus 7, which is 8, and you get 16,000, which is 1.6 microns, which is the H band, and that's where we're studying this. So the universe has expanded by a factor of 8 since light left the galaxy. That's what redshift 7 means. Universe is expanded, and when space itself expands, it stretches wavelengths, including the wavelength of light, and that's why this thing that was emitted at 1907 and 1909 angstroms is now showing up at 16,000 angstroms.
Yeah, I'll just add to one of the things you said, Raja, about the gravitational lensing, about Arya's question. So there's 2 types of gravitational lensing, and I think Anand also kind of made an observation about this. 2 types of gravitational lensing, one called weak gravitational lensing and one called strong gravitational lensing. And I'm by far not a gravitational lensing expert, but the basic idea is that when things, so when distant objects get closer to the mass in question that's doing the lensing, so projected onto the sky, if you can see my video. So if you're observing where you are, and here's the mass in the foreground, in this case, a cluster of galaxies, and you start to move this object around the background, just like if you did it with a magnifying glass, if you move this object in this direction, so along the distance axis, so further away from us, that's going to change the magnification. Just like if you hold a magnifying glass directly up to your face, it's not going to magnify very well. If you hold it very close to the object that you're trying to magnify, it's not going to magnify very well. But if you hold it somewhere intermediate, then you're doing the most magnification possible. So you have your mass here, which is acting as the magnifying glass. You have your distant source here, and the further away it is, generally, the more lensing that will occur. So the more magnification that will occur. And also, if it's closer in projection to the mass. So when it's closer in projection, further away, there's some limit called strong gravitational lensing, where objects will be what's called multiple image. So you'll see multiple images of these objects appear behind the mass that's doing the magnification. And then there's weak gravitational lensing, where it's far enough away from the source, apparently in the sky, that you just get a single arc or a distorted galaxy. And so the object, I think, Patty, correct me if I'm wrong, this object, so we're looking at two galaxies that we're interested in. I believe both of them are in the weak lensing regime. I don't think we think that there are multiple images, and
Yeah,
magnification factors are fairly low. They're maybe factor 3, 4, something like that.
right. Yeah, I don't remember off the top of my head, but yeah, that I know, I'm pretty sure, at least not that we know of, that there are multiple images. Our last target tonight, though, is a triply imaged one, so that's exciting.
Yeah, I was
gonna say
I was
that-
leading into that. So you
Yeah.
wanna
I was just going to say that when things are multiply imaged, there's a beautiful theorem in strong gravitational lensing that says you always get an odd number of images, and one of the images is actually fainter than if it weren't gravitationally lensed. So there's a demagnified image, and the rest of them, an even number, are magnified in the sense of being more brighter than the object would appear without lensing.
I never knew that. And that makes sense with the three we're looking at, because yeah, there's one that's 2 magnitudes fainter than the other two.
Than the other two.
Yeah.
And not only is it 2 magnitudes fainter than the other two, it's actually fainter than the object would appear without lensing.
That is interesting.
It's a demagnified image, and then there are.
Yeah, I didn't even know about the demag. Do you know what causes that?
I remember studying this a long time ago, but
Yeah,
um,
that's sweet. I never knew about that.
Yeah, it's a lot of times how they check lensing models. So especially for galaxy lensing, they because you're trying to get the mass profile really accurately. You'll see obviously the galaxy, the really nice arc in the background of the background galaxy, nice and bright. But then the demagnified image, you don't maybe see in your initial look. And so people look in like the Sloan Digital Sky Survey for these types of sources. And then they go to Keck and they say, okay, well, here's my mass model. I expect to see a demagnified image, at this location when I take a nice long image with adaptive optics with one of the great instruments with Keck called NERC2. And I expect to see an image here, but instead they see images in other places, and that tells you that there's perturbations to the smooth mass
lens.
model.
To the
So
lens,
you
yeah.
see substructure, and so this is how people can both attempt to verify the mass model of the thing that they're looking at, and also see very faint or even dark substructure in the galaxy that's doing the lensing itself. So like Chris Bosnot does this at UC Davis, a professor at UC Davis has been doing this for 15 years maybe, and really wonderful results in terms of finding very, very low mass substructure that's barely visible or not visible at all in cases where a galaxy is lensing another galaxy.
And and Arya asked the question, have perfect circles ever been observed? Those circles are called Einstein rings, and they're never perfect because the alignment is never perfect and the lens is never perfectly smooth. You're talking about a real galaxy doing the lensing. So you get things that are very close to perfect circles, but never a perfect circle.
Yeah, it's even messier in a cluster environment because you have so much substructure. You have all these galaxies. So in a cluster, these fairly old clusters, which are still a third of the way to the edge of the observable universe. You can have hundreds, if not thousands, of galaxies, each with their own halo of dark matter around them. And then you get infalling conglomerations of galaxies, doubles, triples, or even larger groups or association of galaxies that have their overarching dark matter halo. And so there's all sorts of substructure, different. You have this kind of smooth ish mass profile of the cluster, and then you have all the substructure of the galaxies and groups that are falling in or that are associated with the cluster. And so the mass model is very, very complicated.
And
But
actually,
before
Brian,
you-
to use your magnifying glass analogy, sorry to cut you off, to use your
No.
magnifying glass analogy, this is like looking through distorted glass. No, it's like looking through a shower door where you have like distorted glass deliberately so that people can't look in. You get a highly distorted image. It's not, that's why you don't sort of get clean magnification.
Yeah, that's a perfect, that's great, Raja. Yeah, so if you have like imperfections in your magnifying glass, right? Yeah, you just have, you have a certain smooth structure to your magnifying glass, but then you have little tiny magnifying glasses within that magnifying glass. And so it's going to distort everything, and you're going to, things that were you expect to see in a certain location get distorted and moved over to a different location. But the more of these arcs that we can find, and in fact, some of the galaxies or objects that we're targeting in our mass tonight are some of these arcs, and we're hoping to get distances, because as soon as you get the distance, that helps you to better constrain, to better understand the mass model of the cluster that you're looking at.
And Aparajita had a question about the dark horizontal lines. Those are the gaps between the slitlets. Between the slitlets, no light is getting into the spectrograph, and that's why you have those dark lines. And you'll notice that there's that the air glow emission lines are translated left and right from one slitlet to the next, and between them you have those gaps. Aparajita, I think you asked this question, a few questions ago.
Or did
Yeah.
you mean oh, okay. I don't know if they meant like the gaps between or the dark band.
Oh, because it's a subtraction. It's a subtraction.
Yeah.
What you do is you take a spectrum, you then move the star along the slit, and you take a difference between the two exposures. So you get a positive image and a negative image of the star, a positive spectrum and a negative spectrum of the star. That's what you meant, sorry.
Right,
And this
so
kind of sort of nod and differencing is very common in infrared astronomy, because the sky is so bright, the air glow is so bright that this is a great way to subtract off the air glow. That's what you're seeing. That's what Patty's zoomed in on now. That's
Right,
you,
so
Patty, or Brian?
That's Brian.
That's Brian,
kind of team
sorry.
effort over here, I think.
Yeah.
So our star was here. We didn't actually move the star, we moved the telescope. I think, is that right, Patty?
We can't move the star.
We moved the telescope. Yeah. Just checking. I wasn't sure how powerful we were tonight. So yeah, in the last image that we took, this was where the star was, and then we moved the telescope just a bit, and now the star is here. So we get the positive, which is the white, and then we get the negative,
when they
which
heard
is
about the
the black
liftoff,
here.
they got their guns and they went down to the courthouse, not to break anybody out, but the
Yeah, and it's a difference between image A and image B.
Yep, that's exactly right. Yep. And so these air glow lines here, these vertical lines, which are also dark, this comes from emission in the upper atmosphere. And so if we were looking with James Webb or Hubble, we wouldn't see this. But because we're looking from the ground, even at the wonderful site that we're at, there's still this kind of interference from the atmosphere. And the timescale of the variation of this emission is, somewhere between 1 and 3 minutes in the H band. And so this is why, in part, this is one of the reasons why we take fairly short exposures and we subtract the two, because these air glow emission lines vary both on a relative scale and on an absolute scale on these time scales. And so you can see even going just 2 minute frames, you can see how bright they are in the raw frame, first of all. But then even when you subtract the two, you can see that so here there's an over subtraction. So it means that in the first frame, the emission was not as strong, and then it became stronger in the second frame.
So Aparajito has been doing a lot of air glow subtraction, but not in the H band, not in the J band even, but in sort of the 7,500 to 9,000 region of the spectrum. In fact, Brian, he's using Deborah's pipette reductions of some of our masks. So we'd love to
great.
chat with Deborah at some point about
Sure.
just to understand the format of the pipette output.
Yeah, she would love to, I'm sure. She's the person to talk to, that's for sure.
She is the person to talk to, I know.
So we have, what do we have, Patty? We have, we wanted to move to the next target at around 10 o'clock local
Around-
time.
Yeah, yep, that's the idea.
It's
About
about
half
25
hour.
minutes.
Yeah.
So maybe we can end the session when, or like after we move to the next target and then kind of get settled there, so that way people could get a chance to see us move on to our next target and kind of get
Yeah.
aligned and all that stuff.
Yeah, that sounds great. Yeah, and in the plan, we had no mirror between the two because they had similar decks. I'm downloading the 70s of images now, so I'm a little behind, but I think we also wanted to make sure, right, that the seeing was pretty consistent. If we're not going to take a mirror before the next one.
Yeah, you also should look at the temperature value of the primary and secondary mirrors,
Okay.
and those actually look like they've been fairly constant. Same thing for the outside temperature. It's actually amazingly constant tonight. I can show people what we're
Where do you
looking
see
at.
that? Is that in the
Um,
control window?
Yeah, hold on.
There should be a Met. There should be a Met
Oh, it's in
window.
the net.
Yeah, there
Oh,
we go.
yeah.
And at some point, no rush. At some point, I want to answer Anand's question about Hubble's law and the expansion of space-time. I've had to answer this question a lot in my introductory classes that I teach, so I'll take a stab at that at some point. No rush.
Okay, sounds good.
Awesome,
Yeah,
yeah.
so just to finish this thing about the temperature, yeah, so you see the Keck 1 Met down at the bottom right there, and then you
Yeah.
see all the graphs there, so all the different colored lines of the different
Oh,
different temperature sensors and then the dew point. So they have a temperature sensor on the primary and the secondary, and then outside, and then on the dome. And
okay.
yeah, it doesn't seem like things have changed over the last hour or so too much, which is good for to not create seeing cells or turbulence over the primary, which is
Yeah.
bad. So my guess, so what did you do? The mirror you did was how far west of our current target?
An hour.
An hour. Okay, so that's actually not going to be, I should have checked this. So that's not going to be great for our next target because your average air mass, well, it might work. It might work actually.
Okay.
Are you seeing any degradation of the image quality?
I honestly, I haven't been watching it super closely. I'm just downloading the last. Yeah, the last check I did was like a while ago. So it's on the last frame right now, and then I'll run it again and see, I guess, what the seeing has changed. I haven't been checking the raw files though too closely.
Mhm. Yeah, I haven't seen it. It doesn't look like to me that it's been degrading at all. But that's just like a very cursory look.
Yeah.
I don't know, Patty,
Yeah.
so how long are we staying on the next target? It'd be 1 hour?
Yep.
1 hour, and then we're doing our what will be our last target for the night, which will be 6 hours, hopefully, if
Yeah.
everything goes well on max
Yeah.
129.
Yes.
I would suggest since we're only going to spend an hour on 1423,
Mhm.
that we don't do a mirror line,
Okay.
and then we do a mirror for the following target.
Yeah. Okay.
Because the gain, that's a decent chunk of an hour, and so based on what I've seen so far, it's a luxury to do the Mira.
Yeah, yeah. Totally.
Patty, I'm gonna step out for just 1 sec.
Yeah, go for it. Yeah, so Raj, if you're there, I don't know if you want to talk about space-time expansion now.
Happy to do that. Okay, so I'm going to give you two explanations, and they are two perfectly equivalent ways to thinking about Redshift. One way to think about Redshift is if you imagine, you have some three-dimensional pattern of galaxies at some time, and let's say at a later time you have that same pattern, but everything is expanded. So space has expanded, so the distance between any pair of galaxies has grown. If you imagine a scenario like that, it's very easy to see that if everything expands with the pattern remaining the same, it's almost like an enlarged copy of the original pattern of galaxies. The galaxies themselves aren't enlarged, but the distances between them is enlarged. In order to do something like that, you have to have things moving at a speed that's proportional to their original distance. That is, the relative speeds between any pair of galaxies has to be proportional to the original distance between them. V equals h naught d. But another perfectly good way to think about the expansion of the universe is the further apart two galaxies are, say you're observing from one galaxy to another, the further apart they are, the longer it takes light to travel from that galaxy to us, and the longer it takes light to travel, the more time there has been for space to expand. And therefore, the further away something is, the more stretched out its light is. And that's another way to think about Redshift. So I don't know if that answers your question, but that's sort of how I was taught to think about the expanding universe, the expansion of space itself. And Sanjay asked the question, how far back are we now looking at that object? About 13 billion light years. So 13 billion light years away, so we're looking back about 13 billion years. What is the image to the left? Opposite to us. Which image to the left? Oh, this one. Oh, wait, okay. Patty, you've answered that. Guider image.
Yeah.
You
That's a
see
good
beautiful
question.
fringing on the guider image.
Yeah. Yeah, that is really nice.
That's sort of Fabry-Perot fringes.
Mhm. Yeah, and that guider star is helpful because on nights when the weather's not good, like tonight, if there are clouds rolling through and stuff, once we lose guiding from that guider star, that's when we have to redo the whole alignment process with those 5 stars, because then we have no way of knowing if we're off base or not.
True. Sure, no problem. Again, I feel Shadow the Scientist is off to a fresh start with this July 9th run, and it's off to a terrific start. We've had a really engaged audience, excellent questions, and Patty and Brian, you've had amazing description of amazing science. So this has really been terrific.
Yeah, thank you.
Plus the weather has helped out a little bit. and the telescope.
Yeah, that's right. So for those of you who have an experience, as Brian and Patty and I have, for those of you who might be wondering, what would have happened had tonight been snowed out or weathered out in some other way? There are the system is very fragile. If the humidity meter that you're seeing on the screen now if that humidity line were to go up towards 100%, we'd have to shut down the dome just to prevent condensation on the telescope. So sometimes you get shut down by something as simple as high humidity. Everything else is fine, the sky is clear above you, but the humidity is high. Basically, there's a cloud coming up from a level below you, and it's it brings the humidity up to dangerous levels. Sometimes it could be high winds and it's blowing dust that could scrape the mirror. So there's all kinds of things that can shut down a telescope. So what we have a backup plan if the telescope is shut down. We can't show you. We can still show you these instrument controls, of course, but we have backup plans because this is not the first night on the telescope for Patty or Brian or me. So we've collected data in the past, and we can show you either raw data from the past or even processed data where some of the instrumental and atmospheric signatures have been removed. So that's something we've done on nights when the telescope hasn't been able to collect data on that night. No new data were being collected, but you could still explain the experiment and talk about what we've done in previous nights.
Yeah, Brian, I just ran it up to frame 80. And it seems like the seeing's pretty consistent. The median is around 0.65. So
Oh, that's great. Okay. Yeah, and I'm still keeping an eye on the seeing at Gemini. So we have like a running seeing value. And yeah, in the V-band, Gemini is getting something like 0.7 to 0.8. So I think that all sounds consistent to me.
okay, cool.
So speaking of Gemini, and then all the images just went stale. Not a great advertisement for Gemini, but this is a picture of where we're observing. So this is Mauna Kea, and these are cameras that are mounted on the Gemini telescope. So this is on the eastern summit of Mauna Kea, and so there's a camera looking up in the sky, and this friendly thing here is the moon. So moon's about 3/4 full tonight, something like that. And then the North Cam, so this is looking towards the North Plateau. So this is the NASA Infrared Telescope Facility and the Keck 2 telescope. So the Keck 1 telescope is just to the left here, off the camera. And then looking back towards Hilo, which is where I am right now. Can't quite see my house in there because of the clouds, as always. And then a southern camera, so the southern summit, and then looking to the west. And so you can see that things are very, very beautiful tonight. You can see the stars. This animation on the left is a cloud camera, satellite cloud camera. So you can see there's thin, wispy clouds, but not too much cloud cover. And so really gorgeous night, but that doesn't always happen on Mauna Kea. There's plenty of nights that are not gorgeous, and so when that happens, then we unfortunately have to close the telescopes. But for Shadow of the Scientist sessions, we always have stuff to look at. So there's always data, always interesting data to look at, and as Raja mentioned, we will of course share those on the nights that we do end up being clouded out, or if there's humidity or other reasons why we can't use the telescope. Yep, that's it, Jim. Yeah, so Jim just shared in the chat this is a public webpage, so you can just go there and you can look anytime, any night. Usually our cameras, so our meaning Gemini, place I work, the cameras are up and running almost every night. So if they're not running, it usually means it's too humid for them to, so we basically have to shut them down out of danger of damaging the cameras. But every night that the weather's good, you can see what's happening on the top of the Big Island. And in fact, you can actually even see the Maui here. So in the north camera, just off in the distance, you see the clouds passing, but you can see Haleakala on the edge of Maui, so you can see all the way to the next island.
That's cool. I never noticed that.
Yeah.
Can you
They're
point
looking
out
back at us.
Haleakala again, Brian?
Yeah, sure. Yeah, it's so there's this telescope here, which is the infrared NASA's infrared telescope facility, and just above that, you can see there's clouds moving, and then just kind of a nice, like really subtle shadow. That's Maui there, and there's telescopes over there as well. The Pan-STARRS telescopes, which are survey telescopes, are on Haleakala among many others. It's also
There's
very
some
popular.
Air Force telescopes and UH telescopes there as well, if I remember.
Yeah.
How are those cameras working at night? Well, there are sensitive cameras, and they're picking up sort of glow from city lights and moonlight, of course.
Yeah, so much so that they're the moon is blinding the upwards camera. So they're very, very light sensitive. But make for absolutely gorgeous images. And you can actually, you can see clouds very well in these cameras. So we use these when I'm observing on Gemini, which I do, a couple times per month. We use these to assess the amount of cloud cover. And you can get all sorts of really wonderful information with a trained eye with these cameras.
Sweet.
So we're getting there.
Yeah. See, I think the turnover was based on I'm just checking the iObserve image to see.
Yeah, it's a good idea, Ben.
Oh yeah. Oh, okay, yeah. We want to prioritize the one we're on now as opposed to the one we're switching to next.
Exposure complete.
And I see
So
we're
we're
only at
basically
1.7.
riding 1347 down until we can, until like the end of it.
Yeah.
Yeah, that's what it
Um,
looks like.
Yeah, I see we're still at 1.65 air masses, so that doesn't sound too horrible.
Yeah.
So I would keep going.
Yeah.
Yeah, so I was looking back at this S-Max cluster, Patty, that somebody asked about in the beginning of the session.
Yeah.
I don't know if you noticed in the number, it's S-Max J0723.3 and minus 73.27. So this is why we're not familiar with it.
That makes sense. Yeah.
That means it's a minus 73 declination, and basically the limit that we can see to in Hawaii. Let's see, so we're at 20 latitude. So we can, like on the very far edge of the horizon, we can see down to minus 70 declination. So
Oh, that's further than I thought.
yeah, 180 degrees. So so we can't even see it.
Yeah.
So air mass infinity.
Yeah.
So that would be a target. That would be for the southern telescopes, which we don't use very often.
Yeah.
Have you ever observed with the Southern Telescope, Betty?
I never have, no. Yeah, I
haven't
think
either.
I've only done Keck, so,
Yeah, I've only been Northern Hemisphere.
yeah.
I used the Tololo telescope, the 4-meter telescope at Tololo for a large part of my thesis, and then I used the Schmidt telescope there as well.
Nice.
Sweet.
Yeah, we have it-
Where are those?
They're both in as part of part of NOAA Lab. So
Okay.
it was called NOAO back then, and they're two identical 4-meter telescopes. There's the Blanco telescope at Kitt Peak, and there's the Mayol telescope at Kitt Peak and the Blanco telescope in Chile. So it's a little bit north of Santiago, and
Oh,
the
that Atacama?
not quite as far north as the Atacama. So
Okay.
it's south of the southern edge of the Atacama. It's in the headquarters are in a town called La Serena. The headquarters of CTIO still are there. And Magellan's headquarters is also there. But it's a little further north of the telescope's a little further north of La Serena into the foothills of the Andes. But it's not as dry quite as the southern Atacama where the VLT and Paranal are.
Yeah.
There's 3 sets of observatories there, even before they were there before Paranal was built. So it's Tololo, then the ESO telescopes, at La Silla, and then
Right.
Las Campanas, where the Magellan telescopes are.
Sweet. That's cool.
Then, of course, now there's ALMA as well in Chile, which is
Yes.
those are, ALMA and Paranal, I believe, are further north of those 3 sites.
Okay. And do
Yeah,
you
and I
know
think-
where, in relation to those, is Vera Rubin going?
Ruben is very close to Tololo. It's on a separate peak called Cerro Pachon. That's where Gemini South is. Gemini South
I see.
and Ruben are both on Cerro Pachon, which is a neighboring peak from Tololo. They're very close to each other.
Okay.
I've actually been to Pachon before Gemini South was built and before Ruben was built.
Really?
So, yeah.
That's awesome.
That was 2000 or so, yeah, Raja, that it was built.
That's right. So I went there mostly in the late 80s and 90s. And one of your colleagues at UC Davis, Tony Tyson, was my thesis advisor. So Tony and I used to go to Chile a lot together. Tony was one of my 2 thesis advisors.
And what is the altitude of those peaks relative to Mauna Kea? So Mauna Kea is, I think,
14,000 feet.
13,800?
Tololo, if I remember correctly, is 9,000 feet. So it's significantly lower. And I think at peak is 7,000.
Meters?
If I remember right, Alma
No,
is something like
7,000 feet.
14.
Oh,
I think Alma is at something like 15,000 feet, something like that, where it's really, really difficult to
Very
breathe. We have one of
dry.
the operators on Gemini North that that spent some time on Alma and actually had to go do some of the work, on the construction of the antennas and troubleshooting the antennas. And it apparently is very tough work. It's already really tough at 13,800, and it gets exponentially worse from there.
Yeah.
yeah. Wow.
And one of the cool things is at sunset from Tololo, you can see La Silla. You can see the telescopes on La Silla, and then from La Silla, you can of course see Tololo, but you can't see Las Campanas. It's far enough north of La Silla, but from La Silla you can see Las Campanas and vice versa. So they're just about within sight distance of each other. These 3 observatories, these 3 sort of, not even observatory, 3 centers really. Tololo, Pachon being the southernmost, La Silla being intermediate, and then Las Campanas. I've never been to La Silla, but I've observed from Las Campanas, the Magellan telescopes, and from a lot from Tololo.
And what were you observing from there, Raja? Anything interesting?
Lyman Break galaxies. Some of the
Ah,
early
okay.
Lyman Break galaxies work was done from there with Tony and Steve Majeski. This was our first. It was one of the second paper from my thesis was about U-band dropout galaxies. This was a 1990 paper. So long time ago in a galaxy far, far away.
And did you find anything? I know that was during the years where it was looking for these galaxies was very
Yeah,
tough.
so the highest redshift galaxies known at that time were redshift 1, and we placed a limit on what fraction of faint blue galaxies could be at redshift greater than 3, and that limit was about 7 or 10%, because most galaxies were detectable in the U band. And
Right.
I guess the Lyman alpha, well, yeah, the Lyman limit, 912 angstroms, Lyman break moves into the U band at redshift 3.
Mhm.
The U band is at 3600 angstroms, and the Lyman limit is at 912. So at 3 + 1, 4 multiplied by 912 moves it into the U band. That's what we were looking for, is what fraction of galaxies had that happen to them.
Sweet. I'm just gonna interrupt for a quick sec. Do you think we should do one more after this, Brian?
Yeah, I was looking at that right now. So it's gonna, yeah, give me a sec on that.
Okay. So I can just give Julie a heads up about the next one.
Say hi to Julie from me. We don't see her on the Zoom call, of course, but
Oh,
tell her that
yeah.
Raja said hello.
For sure, yeah.
Yeah, Patty, well, I'm checking this real quick. Do you want to tell people who we're interacting with? Because
Oh,
there's
yeah,
people,
these people.
at Keck, which we are not haven't joined us this evening on this call. And so it's of course not just us that's doing the observing.
Yeah, so there's us, we're the scientists that are I guess kind of running these observations, but every night you work on Keck, there are 2 people who work for Keck who are doing observations with you. So there's a support astronomer. So we have Chen Xu is ours for tonight. And he's basically like an expert in the instrument that we're using, and can help troubleshoot any things as they come up. And I always find them like, because I'm always so nervous. So before I click any button, I always ask the support astronomer, I'm like, is this okay to do right now? So it's very nice to have them there in case anything goes wrong and to just make sure everything goes smoothly. And there's also an OA or observing assistant, and they're actually up at the summit at the telescope on Mauna Kea. And they're the one who actually moves the telescope, and they also run the focus for us. So that's Julie for us tonight is our OA. So yeah, we're getting ready to start to switch to the next target. So then we're gonna have to give Julie a heads up because she's the one who actually slews the telescope over for us.
Is Chinsu
Yeah.
your support astronomer tonight?
Yeah.
So say hello to him also. He and I have a co-authors on a ton of ATELs together, astronomical telegrams together. So we work
that's-
together on variable stars.
Oh, sweet. I didn't know that. That's so cool.
So Patty, I would take this up to about maybe 10 more minutes, and then I think we
Okay.
can do a switch out. I think we don't have to go too quick on the switch out.
Okay.
So this is, oh shoot, now I don't remember. Oh no, so Keck 1 is Rising Targets Occult
Yes.
on the NASPET deck, and then yeah, so we can actually follow this pretty far. It looks like the transition between 1423 and 2214, we have a decent amount of time there, so we can actually integrate a little bit longer on 1423. It'll be in the muck, but I think it's
Okay.
more or less all right. So yeah, I would take this one a little bit longer since we're
Okay.
really interested in this target.
Yeah. Sounds good.
And so Julie's doing the hard work tonight. We're not doing the hard work. And she's the one really in charge of this, because she can, of course, shut down the telescope if needed, if there's some weather. So her being up at the summit is really helpful. She's our eyes and ears up there. And anytime we want to move the telescope, she's in control of that movement.
Mhm.
So it pays to be nice to your telescope operator.
All right. Well, I'll just give her a little heads up that we're trying to move in about 10 minutes, if that sounds good.
Yeah, that sounds good.
And Jim, You're absolutely right. Tololo is at 7,000 feet, which is 2,100 meters, and 9,000 is the mid-base level for Mauna Kea at Hale Pohaku. That's what I was mixing those two up. But it's significantly easier to operate at Kitt Peak and Tololo than it is at Mauna Kea in terms of oxygen deprivation.
Absolutely, yeah. There was a question from Joan, if she's still in the call. So there was a question about the software, how much software that we write, especially for ourselves, and how much is standard. So everything, Joan, that you see here, this is not stuff that we've written, but it's rather software engineers or support astronomers, usually some combination of the two, at the observatories. So the observatory that I work at, Gemini North, I do a lot of the software development for the tools that we use for our observing. And similarly at Keck 1 and Keck 2, they will develop the software so that we have this really nice, easy to use interface. So back in the day when, even during my graduate thesis, but you know, Raja observed much earlier on in Keck's history than I did, there were these really nice graphical user interfaces for us to use. And so, you know, we were struggling along with some pretty clunky software, trying to make sure that we were in the right part of the sky. And I remember, you know, bringing binders of printouts of finder charts to make sure that we could orient in the sky well. And so that's changed a lot over the last 2 decades. And so we have this really nice setup that we can point and click. And of course, if things go wrong, we have to go into the actual code. But a lot of times it's just this nice graphical interface that we can use. And that's thanks to people developing it at Keck. So it makes it easier for people like us that come and visit with Keck to do science, to be able to do that without having to worry too much about the under the hood kind of stuff for the code. But of course, for our scientific purposes, there is developed code for measuring a lot of things. So Patty was showing, for example, this, the last plot that she showed was something called EW, or equivalent width. There's standard codes that can be used to measure the strength of a line in a spectrum, but you may want to modify those for your purpose. So maybe the standardized codes, these are all written by astronomers usually. Astronomers are notorious for not being super awesome at coding, which includes myself for sure. Patty's awesome, but I'm a little bit stuck in the dark ages on certain things. But I write my own code just really poorly, and for my own purposes. And so you want to make sure that whatever analysis software that you're using is correct for the scientific question that you're using. And so somebody will create an ad hoc program for their purpose, which if you use it blindly may not work for your purpose. And so a lot of astronomy is developing codes that can properly analyze the data in the most in the most sensitive way possible, because time on the telescope is very, very precious. You know, as Patty mentioned, we had 3 nights this semester for this project. That's great. That's really exciting. But it's only 3 nights. And so, you know, that's a total of maybe 24 hours of observations. And then we spend a lot of time trying to dig through those observations and extract the information that we want. And so we spend a lot of our time trying to make codes that are optimized that can give every little piece of information out of the observations that we're taking. And so then once we get that, we extract that information, then we go to models, so models of galaxies or models of the universe. And so Patty's last paper was exactly this. So making measurements on the data, getting measurements of strengths of lines or non-detections of lines, and then comparing that to models of Lyman alpha emission at very early times in the universe's history. And so Patty worked with somebody called Charlotte Mason, who is now at Copenhagen at a place called the Dawn Center, to develop those models and then to test the observations versus the models, and then extract information about what the early universe looked like. And Charlotte coded all that stuff up, and it was based off of physics and scaling relations in physics, and simulations of galaxies at early times. So that's all developed for by astronomers, basically by themselves or as a community, and we use a variety of different programming languages for that.
Yeah. And yeah, Jim, I'll echo what Raj just said. I like exclusively use Python. I only know IDL well enough to read Brian's codes and try and figure out what they're doing. So
Oh, that's so sweet of you, Patty.
yeah.
Yeah, and I'm the reverse. So I program mostly in IDL, but in an observatory environment, you need to know a lot of different languages. So we primarily use Python at Gemini. So I've only been working at Gemini for about 10 months, but I've had to learn quite a bit about Python over that time. That's the wave of the future for sure, if not the present.
Yeah.
So Patty, should we stop after this repeat? I see we're getting 1.8 air masses. We could also go one more if you want.
Yeah. I mean, it doesn't matter if we're on the A or B nod position when we finish, right?
Not really. It's nice to get an A and B, but it's all good.
Yeah.
Maybe we'll go one more after this.
Yeah, we
One
can
more-
do one more.
We'll
Yeah.
do one more repeat. So maybe I think you can just change it to 13, maybe, and
You think you'll do that?
I don't actually know if that changes. So
See, I want to press this drop down menu, but I'm scared I'm gonna do the wrong thing. Press the board after frame instead. But I feel like if you drop down, there's a board.
drop it
after-
down. Drop it down. It's okay. Go ahead.
Okay. Yeah, board after repeat.
Yeah.
So
So
once
that would
this
be
next one starts, should we do that?
Yeah, you could also do a board after frame on the B exposure. That would be totally fine. But yeah, that should work. That should work as well. So once you start the next exposure, then do a board after repeat, and then it just has to be smart enough to know when our repeat is done.
Okay. Yeah, hopefully that works.
And Jim, IDL requires a paid license, which is another reason why it never really took off.
Okay, I'm gonna try the board after repeat.
Do it.
Trying something new.
I'm
So
going to
think
sign off soon, Patty and Brian, to sign off. I know it's been a little over 2 hours for our STS session, but I'm going to let you guys go on with these wonderful conditions, find some C3.
Yeah.
Awesome. Thank you,
Hopefully.
Raja.
Yeah.
Thank you. Thank you. This has been terrific. Really been good.
And thank you for the positive thoughts of finding C3 emission. That would be wonderful.
And
Yeah.
thanks to Vicky, we had a couple of people who connected from Botswana. Vicky herself is in Mount Botswana right now. But I think Shipa is, I hope I'm pronouncing your name correctly, is from Botswana. And of course, Arya, it's so great to have you back. We have some SIP interns who connected. I see Yael on the call. We've had several others earlier in the night. Nishant, Pranav was here earlier. So we have several students from our current summer program. We have UCSC faculty member in Matt here. So it's very nice to see a great collection of people. Yeah, we have about somewhere between 30 and 50 Shadow the Scientist sessions coming up just between now and the end of 2022, the second half of the year. I think it'll be close to 50. And what we're going to do is we'll have a bunch of open sessions like this where we'll advertise the sessions, we'll put the registration link on the website. And what we're planning to do is have a few dedicated sessions where we reach out to specific groups and just dedicate the session to them, and it might be a set of high schools, for example. It might be a group that's doing, for example, we're involved in some kind of science internship or there might be students from a particular university. So we're thinking of doing some dedicated groups as well. And the advantage of that is there'll be a sense of a cohort of people doing this together who can then interact afterwards and share their experience and sort of deepen the experience through pre and post interaction after they've taken part in, before and after they've taken part in Shadow of the Scientist. So that's our plan. Yeah, thanks, Brian. That's yeah. There's I mean, you'll see of order 30 dates listed in the on the website that Brian just pointed to. And some of those nights we may be doing more than one session, one early in the night, one late in the night, because I realized that the time slot we picked today, early in the Hawaiian night, was sort of late in California and sort of impossibly late on the East Coast, and actually difficult for, possibly difficult. Yeah, I mean, I guess it was really difficult for the East Coast. But so if we did something late at night into the wee hours of the night in Hawaii, the end of the night in Hawaii, that would be ideal for the East Coast, because then it's, people are, up and about in the morning. There's a 6-hour time difference right now between Hawaii and the East Coast. So something like a 3 to 5 a.m. in Hawaii would be like a 9 to 11 on the East Coast. One of the things that I'm exploring, Brian, and this is something that just a conversation that started on Friday, is there's a group called SACNAS. I'm going to put the name in the chat. Patty and Brian, you may have come across SACNAS. SACNAS's annual meeting is in October 27th, 28th, 29th, and they're going to be meeting in Puerto Rico, which is the same as East Coast time. So it turns out we have a STS night on October 28th, and that's in Hawaii. And so if we did something near the end of the night there, that would be 9 to 11 a.m. in Puerto Rico, and we might be able to embed this into the SACNAS program so that people attending the conference would have this opportunity to take part. So we're just exploring this right now.
Wonderful. That sounds
SACNAS
great.
stands for Society for the Advancement of Chicanos and Native Americans in Science. It's
Yeah.
actually, I'm
UC
proud to
Davis-
say.
UC
Say that
Davis has
again.
a big UC Davis has a big partnership with that, and I think the Physics and Astronomy department has attended SACNAS meetings in the past and has had various programs in conjunction with the society.
SACNAS is a terrific society, and I'm just proud to say that it was started in the town of Santa Cruz. Nothing to do with UCSC. It was SACNAS originated in the town of Santa Cruz, and I've been to one SACNAS meeting in San Jose, but so I'm working with someone who runs our American Indian Resource Center at UCSC. She had the idea that the SACNAS meeting might be something we could pair with Shadow of the Scientist, just like in the same way that we did with all space considered from Griffith.
Yeah, that was wonderful, Raja.
That worked out well.
More of that would be great.
Yeah.
So I'll just interrupt you for a sec, Raja. So Patty, actually, you can unmute. You're fine because I'm muted and I have my sound off on the other Zoom. So maybe we'll have a chance to hear you interact with the summit.
Yeah, for sure.
Yeah,
sorry, I was just muting for.
No, that's great. That's great. Yeah, because the feedback can be pretty crazy. But yeah, so I guess we're moving on to our next target. So this is the one that's highlighted there. So we were observing the fourth target, which was highlighted in blue on the screen that I'm sharing. And we're now moving to this one highlighted in yellow, which is a different cluster of galaxies at a different right ascension and declination. And so we're seeing the guider image basically update its reading out, and the streaks are stars or galaxies moving past the detector as we're moving the telescope around. And simultaneously, Patty is changing the instrument. So loading up our new slit mask. And so all those configurable slit units that I talked about earlier, they're gonna have to start to change because we're doing a different orientation, different part of the sky, and we're looking at different targets, although the same types of galaxies. So I'll just kind of
Okay,
cycle
thank
around
you.
the different screens.
And you can start the alignment for guiding.
Awesome, thank you. Perfect.
So you just started the alignment mask.
Yep.
Sweet.
Patty, sorry for yakking away while you were trying to communicate.
No, it's all good.
Are
It's
you
all good.
good?
All of this is
Um,
important.
Yeah, should I grab this guider image?
Sure, yeah, you can, yeah. So I'll just, for people that are still following along, so this is some movements that we're making. This is the CSU status bar, so configurable slit unit status. And so you can see all these, if you can, if it's apparent on your screen, you can see all these vertical lines that'll be moving, and these green slits will show up in new locations. So this process takes about anywhere between 3 minutes and 5 minutes to do.
And just move it?
Oh yeah, Patty, yeah, you can move.
Awesome, okay.
Let me see.
And you're getting ready for a new patch of sky, basically.
Yep, exactly. And Patty's here, let's see, I'll move over to another screen. So Patty, do you want to show that that course line thing? Kind of
Oh, yeah,
run
yeah,
down.
yeah. Oh, sorry about that. Yes.
Oh, it's all good.
Yeah.
There's a lot going on. This is the exciting
Yeah.
part of the night. This is when everything happens.
Yeah. Like twice a night, you get something to do.
If you're lucky, if everything goes well, then yeah, we have a very calm and
Yeah.
easy night. Yeah, so I guess you were just grabbing a guide. So the image on the left there was like an archival image of from a survey from a long time ago. And so we're just trying to match up in the sky in a very coarse way what we see. So the image on the right is an image that we just took with the guider camera. And the red and white boxes are the expected locations of the stars, and then the found locations of the stars. So you can see the red and white boxes are basically on top of each other in this image. So we think we're in a good place. And so that'll get us within probably 2 to 3 arc seconds, which is maybe an 1800th of a fingernail width at arm's length. And so then we're going to go on to this final line process as soon as all of the configurable slit units are moved, and we're going to look for our alignment stars in our boxes. So in five of the configurable slit unit pairs, we're making boxes that are about I think about 4 arc seconds, at least in DMOS, they're 4 arc seconds wide. And we're looking for these brighter stars to show up in these boxes. And if we can see them show up in these boxes, then we center them, and then we try to align to better than, let's say, 1/10 of an arc second.
Brian, I like your fingernail at arm's length. The other thing that might be relatable is 4 arc seconds is 1/500th of the diameter of the full moon.
How many arc seconds is that?
4 arc seconds, the size of a alignment box is
Yeah.
about 500 times smaller than the diameter of the full moon.
Yeah. That's good.
Yeah, that's a good one.
Okay, almost there.
Almost there.
Yeah.
Whoa. And Patty, I think we can go a little bit longer than we planned on this field, just to make it worth it.
Okay,
Because,
yeah.
yeah, I mean, we were basically moving to 21, 29, the first possible second that we could, but
Right.
with the Mira, we're gonna be at like, I guess we'll pick it up at like 1.8 air masses. And
Okay.
yeah, we definitely don't want to get there early. So
Yeah.
yeah, I think we can take a little bit extra time.
Okay.
What's our integration depth on this?
What's our
Like,
what?
Our integration depth. So like, let's say 45 minutes versus an hour and 15 minutes. Is that going to make a difference? Or are we kind of in the area where that doesn't make a difference for this field?
What do we have so far? Oh, we already have 7.5 hours on this guy.
Yeah. We have nothing on 21, 29, right? This is our one shot at it.
Yeah.
Okay,
All right, I'm gonna start this final line.
sounds good. I'll share that screen.
Yeah, the biggest thing for 1423 is the nature paper one, the 7.64 is really bright. So
Yeah.
this, I mean, it would be probably like what, like a 1 angstrom difference, I think that we would get.
Yeah. The gains are limited.
hour.
Yeah, the gains are limited. Yeah.
Yeah.
Yeah. So okay. That helps. So let's see. Okay, so you were basically having us go to 21, 29 like the second it rises above the Nasmet deck, right?
Yeah.
Yeah. Okay, no, that's good. That's good.
Yeah.
And that would mean about 40, well, yeah, about 45 minutes on this target. I think I would actually say that's okay.
Okay,
Half hour, 45
so
minutes.
take this until like 11:15.
Yeah, 11, 10, 11, 15. Yeah, I would say so. Mira should only be about 6 to 7 minutes. So
Is this
you budget a
going?
little bit of extra time.
I don't know if this is, should I press it again?
You can open up the IDL window and see if it's running.
Where
It
is
is not taking an exposure, so yeah, it might have crashed. So
All right, I'm just gonna try again.
do you mind if I take over for a sec, Patty?
Oh, yeah, go for it.
Okay, it somehow it it failed to pick up a Mossfire keyword, so it didn't.
Oh,
Yeah, so it got some weird conflict where it thought it was going to the dark filter rather than the J imaging filter. So just
oh, it's exposing now.
button IDL hang up, yeah. But yeah, always good to bring up the IDL window just in case things aren't going. But yeah, good catch.
Sweet.
Exposure complete.
Anand, what is 7.2 arc seconds there? Just curious. I noticed you typed that into the chat.
So this is an image here of this is a direct image of our mask, our slip mask, and you can see the little slits here. These are our alignment boxes, and we actually don't expect to see anything in the alignment boxes in this image. This is a sky image. And now we're taking it, so we've moved the telescope away from the stars and all of our targets and slits, and we're now taking a direct image of the sky where we are hopefully pointing at our targets. So the next image, we should see the stars, and then we subtract the two so that we can pick the stars out of the noise.
Complete.
And I see some stars. Nice.
Some stars. All right, should we send moves and retake?
Totally. And those profiles still look pretty good. They're fattening out a little
Yeah.
bit, but I think
Yeah.
it'll last for another half hour, 45 minutes.
Yeah.
I hope.
Oh yeah, they're pretty offset in the boxes, eh?
Yeah. Let's go. It's good to be defined course line though. Aloha, Arya. Thank you for joining us.
Thank you. Oh, this just got this one.
Closure
Oh, there we go.
complete.
All right. That's good, right?
Oh, that's great. Yep. Mhm.
Awesome. Go dark. Setup sign.
Wow, it's not often we get these one shot alignments. This has been nice to me.
Yes, this is dope. I picked some good stars.
Totally. Yeah. That was your awesomeness.
Alright, everything else should be the same. We're still at 1.25. 13 repeats. I'm just gonna give it 10. I guess. Oh, we get to
I would do a lower number, Patty, so we can just kind of, so that way we don't have to do the abort, because always doing the abort is a little bit sketchy.
Yeah,
Although it did work that time, so that was good.
yeah. This is good to execute, right?
Yeah, we're at a drive angle of minus 100, so yeah, we're not in the danger zone. So now we're moving to our science mask, so that we're taking the stars, star boxes that we had, and we're moving them to scientific targets. So I think 4 out of the 5 will move to scientific targets, and then 1 of the 5 will keep will make a slit on the star to track our image quality
Yeah.
and the telescope over time.
Oh yeah, Julie, could we mark base here, please?
Thanks, Patty.
Do you do this by changing the slit configuration or by moving the telescope?
It's correct.
Awesome, thank you.
The slit configuration.
Gotcha.
Yeah, so you can see that let's see, 1, 2, 3, 4, 5 configurable slit unit pairs are moving right now, and those are all ones that have this little bit wider opening. I'm sure it's hard to see on the screen that I'm sharing, but a little bit wider opening. So those are the boxes, and we're making slits out of those.
I see. And those are, and you keep one of them on, you keep one of them as an alignment box on a star.
Exactly. Yeah.
So this
yeah.
this one started with 7. It's going to end up with 1.
5 total usually, and then end up with 1. Yeah.
Oh, okay. Okay.
And so it'll be, I think it'll be this one down here.
This is something you can't do with Demos.
Yep.
Mhm.
Takes a long time, but it's worth it.
Right.
Ooh, that's a little bit weird.
Gonna go
a little bit
ahead.
weird.
What'd
Patty,
you
do you see the CSU's
Oh.
60?
I thought you did that.
No, sorry, it's just a GUI thing. Nope, that's a
Okay.
really weird. I wish that was a different color. I wish that were a different color.
All right, so
It
we're
looks
good
like
to
the
go, right?
CSU is like completely open. So yeah, I think you're good.
Okay. Switch the page.
Oh, I
Okay.
didn't even know you could interact with that like that. That's interesting.
Yeah, I was just gonna say, I didn't know you could do that.
Yeah.
That's sweet.
Okay, we're off again.
Yay. Cool.
So that was the life cycle of an observation. So we made it through our first target. We spent what about almost 3 hours there.
Yeah.
Collected some amazing data, I think. We'll know hopefully tomorrow, but when you wake up, Patty.
Yeah, I mean,
and
I'm
we did
good. I was
anything
gonna start running that reduction anytime now, so
Awesome.
maybe even
Okay,
before the
yeah.
end
So
of the
maybe we'll
night.
know
Yeah.
later tonight.
Yeah.
Whether we see anything, and you'll combine that with the data that we took other nights, right? So we have
Yeah.
already a decent amount of observation on other nights, so we'll be combining all those data. We didn't see anything in the first data, but maybe with the combined power of these couple nights that we'll see something. And yeah, so now we're moving on to our next target. We're starting to take some observations. It seems like the night has been amazing and will hopefully continue to be amazing.
I wanted
But
to
yeah,
give a shout out to Julie and Chinsu.
absolutely.
Please
Yeah.
thank them on my behalf.
Oh, yeah.
Thank you, Yael and Nishant. They're both in our SIP program. Moletlanye and Lefika are connecting from Botswana, I believe. So thank you for being here. I really appreciate it. It's gotten so late here that my time lights in my room have gone off. You're seeing me in the light of my laptop screen. I had to turn up the brightness of my laptop screen, not so I could see it, but so you could see me.
And conversely, Raja, I'm about to go have dinner. So
Okay.
the life cycles of astronomers.
I will call
I'm
it
just saying
tonight.
that. Yeah, so the a little bit different time of night for me here.
It's true. It's about 1:30 here, but I really appreciate everyone. Brian, Patty, you guys are amazing.
Yeah, it was our great pleasure, and I'm so happy that we had so many people interested. The questions were absolutely amazing. It's a real pleasure for us to be able to talk about these things. Everybody asks us challenging questions, and it makes us think more deeply about our research. And so it gives me energy to be on the telescope for a long night. This is why we do it at the beginning of the night. Although, yeah, we're going to switch some sessions to 3 to 5 in the morning, almost certainly, so other people can join. And so hopefully that'll get my neurons refiring at that time of night.
And Jim and Rodri, welcome back. You guys have been faithful participants in STS. So.
Thank you for keeping me on the list.
Oh, we will always.
And Raja, the next session, do you happen to know when that is off the top of your head?
August 3rd. It'll be using the Lick telescope at Mount Hamilton. My undergraduate student, Stephanie Figueiredo, will be at the telescope on the mountaintop. There'll be a science team that includes Monica Soraisam at Hilo, Kevin McKinnon at Santa Cruz, and Rafael Nunez in Santa Cruz, and myself, Los Altos. So that'll be on a California telescope. So it won't be quite as late on the East Coast. We'll start that around 8 p.m. or a little after that, I guess 9 p.m. California time. So it'll still be late on the East Coast, but not quite as late as this one.
And I'll just mention that Monica is a fellow Geminite, so she's at Gemini North with me.
In fact, Monica, Chinsu, and I collaborate a lot.
That's so cool.
Yeah, and that's one of the wonderful things about astronomy, that it's a friendly competition between all the telescopes, and there's a lot of cross-pollination, cross-collaboration. I'm observing on Gemini all the time, but I'm also observing on Keck and Subaru. Raja has observed on many of the Mauna Kea telescopes and telescopes all over the world. And it's a very wonderful community where there's a lot of cross-pollination for scientific ideas and using different types of instrumentation to realize those ideas.
Exposure.
So we have 3 nights in August, all on the Lick telescope, and there'll be August 3rd, 19th, and 28th. I'm putting this in the chat. We'll all be on the Shane telescope at the Lick Observatory. Sorry, Shane spectrograph Shane Telescope cast spectrograph at Lick Observatory. We'll be taking spectra of variable stars in Andromeda. And then we have a string of 9 nights in September, during which we'll do STS sessions. Actually 10 nights, September 18th through September 27th, both inclusive, those 10 nights in a row. we'll
I hope
run
you're getting some
STS.
help for that, Raja. That's not all you. right?
It's multiple projects, multiple people. So yes, I'm probably going to go out to Hawaii for that one. But there'll be a bunch of people. Evan Kirby's involved. Marla's involved. Marla Jeha, Dan Wise, myself. So a bunch of us.
Nice.
September will be a
Okay,
busy
well-
month. Yeah, sorry. Go ahead.
I think we've reached the end of this session, only because I need to go have dinner to not fall asleep at the telescope. So thank you everybody for coming. And we will see you again at another Show of the Scientist session. And Raja, thank you so much for staying up.
Oh, thank you. Thank
As
you for having me.
always, being our star of wisdom and shining light for these sessions.
Oh, thank you.
Yeah.
And I'll
thanks
see
for
you in a
coming,
second,
everyone.
Patty.
This is super fun.
Okay.
Yeah, I'll see you.
I guess you'll stop the recording, Brian, and
I will.
continue. Okay. And then thanks, everyone. Take care.
Okay. Bye, everybody. Aloha.
Night.
Bye.